video that Claudio will do, which might not come through so well in Zoom. So you can also just download it and watch it. It's a short thing. So, you know, if we can have an active discussion in the chat, that'd be great. People can respond and discuss, and then any questions that need to be brought to Claudio's attention, I can bring. At the end of the talk, we'll allow people to unmute themselves, and everyone can join together and applause, and then ask questions there just by talking. Okay, so Claudio will be speaking to us about metastability as Markov chain model reduction. And Claudio, if you want to share your screen and then start.
Yes. So can you see my screen? Yeah. Okay, perfect. So, well, thank you very much for the invitation. So I'll be talking about metastability, and I want to start showing you a video which well, exhibits exactly the phenomena which I want to talk about. So this is a super cooled water, and it's at -2 centigrade, and you'll see that a small perturbation in this super cooled water will transform it immediately into ice. So this is what you are seeing. You'll see it again in a second. And this is available on YouTube. It's from the European Synchrotron Radiation Facility. So this is the phenomena which I want to talk about. So you have some system which looks to be on a stable state, but a small perturbation transformed it. So it wasn't really on a stable state, it was on a metastable state, and then it turns to the stable state. So this is the content of my talk, and I will divide it in 3 parts. So I'll describe 2 models, the Ising model with the Glauber dynamics, then I'll turn to the zero range dynamics, and to illustrate the theory which will be presented at the end. So at the end, I want to state a theorem and give a sketch of the proof. And this theorem is based on these 2 models. Insuk will talk later on more precisely on these talks. So on these models. So let me start with the Ising model. Here are many references. I won't spend time on that. You can look at this reference and at the slides of the talk later if you wish. So here is the model. So we start with fixed L. L will be fixed. It's large but fixed for all this talk. And you consider a 2-dimensional torus of length L. So this is lambda L. So mind you, you have periodic boundary conditions here. And on each side of this torus, you have magnetization, which can take the value -1, 1. So the set of configuration, it's -1, 1 to the power lambda L. And I will represent these configurations by sigma. So for point X in lambda L, sigma X will take the values ± 1. And what's the important object here? It's the energy. So to each configuration sigma, I will give an energy, which I'm representing by H. So H, it's the energy of this configuration. And what you do here is that, well, you take all nearest neighbor. So here the sum runs over all nearest neighbors sides. And you multiply the magnetization of these 2 sides. So if they are equal, you get a +1. You want the energy to be minus. So if sides with neighbor sides have the same magnetization, this will decrease the energy. And this is what you want to minimize the energy. And also I'll fix a parameter H, will be non-negative, which is an external magnetization. And so you see that the spins will try to have the same sign of H. So here I'm taking H non-negative, so the sigmas will try to be, well, if you want to minimize the energy, they'll try to be positive. And to that energy, so I'll define the Gibbs measure associated to this energy, which is to take the energy to the, well, multiplied by beta. Beta is the inverse temperature. Beta will converge to +infinity, so beta is very, very large. And well, as a weight, you put exponential minus beta h. So you see that if beta is very large, you're giving more weight to configurations in which minus h it's very large, so h it's very small. So this is what I said. You want to minimize h, the energy of a configuration here. So h will be fixed, lambda will be fixed, and the parameter you playing with is the inverse temperature. It's beta. Beta will converge to plus infinity. So you see, the first object you want to see, it's the configuration which minimizes the energy, and the one which minimizes the energy is the one, since I'm taking, say, H strictly positive, the one which is minimizing the energy is the one configuration in which all spins are positive. And then I'll define the dynamics, the Glauber dynamics. And these dynamics do this thing, it flips a spin at a certain rate. So sigma x will represent the configuration sigma in which you flip the spin at x. And you do that with a certain rate. Which rate is that is what I will describe now. Well, this is the formula, but to explain this formula, let's take two configurations, sigma and sigma prime, and they differ only at one side. And assume, so here I wrote sigma, so I assume that the energy of sigma is larger than the energy of sigma prime. This means that you will jump at rate 1 from sigma to sigma prime. So you decrease your energy, you can decrease the energy at rate 1. On the other hand, if you want to increase the energy, you do that with a very, very small rate. So this is done at this rate. Well, you compute the difference of the energies between sigma and sigma prime, you multiply that by beta. So this is a positive number. You take the minus and exponential of this. So since beta is large, these rates are very, very small. So with rate 1, you decrease the energy, and with a very small rate, you may increase the energy of a configuration. And why do we choose these rates? Well, because they satisfy the detailed balance condition, which means that the measure I introduced before, it's reversible with respect to these dynamics. And what we want to investigate is how these dynamics evolve in time. So the first thing we want to study is, well, the energy landscape. So we define this energy. Let me assume for now on that H is strictly positive. And as I said, you have one configuration, which is the ground state, which is the configuration in which all spins are +1. And well, let me represent by -1 the configuration in which all spins are equal to -1. So here, remember, it's the formula for the energy. And well, since +1 is the configuration which minimizes the energy, one thing you know is that if you send beta to infinity, the measure will concentrate on that configuration. So this configuration concentrates essentially all the measure of the stationary state, if beta is large. So now you start from a configuration, and as you see, if you decrease the energy, you do that at rate 1. So I would like to find configurations which are local minima of the energy. Because if you are in a configuration which is a local minima, well, you don't jump at rate 1 to another configuration, but you jump at only very small rates. So this tells you that in some sense, these configurations are metastable, so that the process will remain a very, very long time in these configurations because you jump only at an exponentially small rate to another configuration. So here I draw a configuration sigma, which is a rectangle of pluses in a sea of minus. So what you have to think is that, well, this is surrounded by a sea of minus spins. And well, now let's compute what is the rate at which this configuration jump to another configuration. So there are two critical situations. The one in which you move, we flip a corner of this configuration. So you turn it from plus to minus. So I represent it by sigma prime. And let's compute the difference in energy between sigma prime and sigma. So here is the energy of sigma prime. So you see that the number of bonds between a plus and minus did not change. So if you count the number of edges which separate a plus from a minus, this is not changed by flipping this plus to a minus. So this piece of the energy doesn't change. Well, it's the same from sigma prime and sigma. The only thing which changes is the fact that we have here a plus and here a minus. And since H, it's, so you see that the difference between the energy of sigma prime and the energy of sigma is that you're flipping one spin from plus to minus. And this will give you that the energy of sigma prime, it's actually equal to the energy of sigma plus H. And since I'm assuming that H is strictly positive, this means that this energy is strictly higher than the energy of sigma. So this is one case. Another critical case is this one in which you flip a minus to a plus at the boundary. So now we are, by doing that, we are increasing by 2 the number of edges between minus and pluses. So this explains that you have this plus 2 when you compute the energy of sigma double prime, but also you transform a minus to a plus, so you have a minus H contribution here. So the energy of sigma prime double prime, it's equal to the energy of sigma plus 2 minus H. And if I want to turn this configuration a local minima of the energy, I want this quantity to be larger than the energy of sigma, which means that H has to be smaller than 2. So from now on, I will assume that H, the external magnetization, is between 0 and 2, strictly between 0 and 2. And that turns this configuration a local minima of the energy, which means that if you reach such a configuration in which you have droplets of pluses in a sea of, I'm sorry, here is it. So if I have a droplet of pluses in a sea of minus, these configurations, and of course I may have more than one droplet, you can have many droplets but very far apart one from the other, and these are local minima of the energy, which means that if the process reach one of these configurations, it will remain there for a very long time. So one thing on the other hand, if you do the same, of course, I didn't analyze here all possibilities, but you can do that and reach this conclusion that these are the only local minima of the energy. And on the other hand, if you analyze the droplets of minus, you can conclude that they will disappear. Which means that you have a path in which the energy decrease until you reach a configuration in which you have only pluses. So the +1 configuration. So this tells you, so the conclusion is this, that these are the local minima of the energy. Well, so what you expect is that starting from any configuration, you reach one of these local minima pretty fast, because you can do that by jumping at rate 1. But once you reach a local minima, you stay there for a very, very long time. So how to analyze that dynamics? What you can try to do is to examine the dynamics only when the process reaches one local minima. So forget about all the other configurations and observe your dynamics only when you hit one of these local minima. And then you have to analyze how you go from one local minima, say sigma, to another local minima, say sigma double prime. So either this droplet will increase or it will decrease. So let's see what happens, what you have to do, what is the path you have to do to increase your droplet. So this is what I'm drawing here. So this is a droplet of pluses in a sea of minus. If you want to reach sigma double prime, what you have to do is first create, flip a minus to a plus at the boundary. And as you see, as we have seen, the energy of this configuration is the original energy plus 2 minus h. And once you do that, you see that now, in order to go from sigma prime to sigma double prime, what you need to do is to flip these other neighbors. And when you do that, you don't increase the number of edges, but you only change a minus to a plus. So this means that starting from sigma prime, the energy only decreases until you reach sigma double prime. So the maximum energy in this path, it's reached at this configuration sigma prime, and its value, it's given by the original energy plus 2 minus h. So the maximal energy in this path, it's given by this expression. So, and you can show that the rate at which you jump from sigma to sigma double prime, it's proportional, well, it's exponential minus beta, but proportional to this difference of energy. And note that, well, this energy doesn't depend on the length of the rectangle. So this describes how you, well, the cost of increasing a droplet. So now let's analyze the cost of decreasing a droplet. In order to decrease a droplet, what you'll do, it's that, well, you'll first, the cheapest thing to do, it's first flip a corner and then follow flipping a second object, a second magnetization, a second spin, and at last a third. And now what is the maximal energy in this path? Well, you see that you didn't change the number of edges between pluses and minus in this transition, but you change a plus into a minus. And you reach, until you reach this configuration, so let me call small l the smallest length of the rectangle, capital L the largest length of the rectangle. So after flipping L minus 1 spins, you reach a configuration, which is represented here by sigma L minus 1, in which the energy is equal to the original energy plus L minus 1 times H. And so this is the maximal energy in this path, which goes from a configuration local minima sigma to a local minima sigma double prime, in which you removed one side of the rectangle. So now, if you want to observe the dynamics along these local minima, and if you accept the fact that the jumps among these configurations are proportional to the energy barrier, you have to compare what's the cost or what's the rate at which you increase, which we obtained that it's given by this expression, with the rate at which you decrease. So we have seen that the rate at which you decrease, it's easier to decrease, to remove the smallest length. So that means that in the rectangle, the largest length will decrease by 1. So the rate at which you go from a rectangle LL to rectangle LL minus 1 is proportional to this rate, to this exponential. And this means, therefore, that it's easier to increase if this expression here, it's smaller than this one, which means that, well, if you take the h to the other side, which means that 2 over h should be smaller than L. So let's assume that 2 divided by h, it's not an integer. Let me call the critical length LC as the integer value of 2 over h. This means that if L it's smaller or equal to this critical length, it's easier to shrink the rectangle, while if it's larger than LC, strictly larger than LC, then it's easier to grow with. And therefore, there is a critical droplet, which is this droplet which has one length equal to LC plus 1, the other length LC, and one extra positive spin at the longest border, because at this point, it will take you a rate 1 to complete this row. And once you reach this square of size LC plus 1, it will be easier to increase that than to decrease it. This means that if you ask yourself what happens when you start from -1, which is a local minima, and you want to observe your process until it reaches the configuration +1, well, if you start from -1, what will happen is that you will create some droplets, but these droplets will have a tendency to shrink instead of growing. But if you wait long enough, at a certain point, you will create such a droplet, which is a critical droplet. When you create that droplet, two things may happen. Either this plus transform to a minus, and therefore you shrink again to -1, or and this happens at rate 1, or you fill this row. In this case, you attained a supercritical droplet, which will increase to +1. So this is a first order graphic of what happens. You have a -1, all spins equal to -1, which is the local minima. The global minima is of the energy. So here I'm drawing the, a picture of the energy. So +1, it's the global minima. If you start from a droplet which is subcritical, you'll converge to -1. This subcritical droplet will decrease, will shrink up to -1. And starting from -1, at some point you create droplets. At one point you'll create this type of droplet, and there you have a positive probability to jump to +1. So that's a model which tries to describe this metastability phenomena, in which you spend a very, very long time -1, until at some point you create a perturbation which is large enough to drive you to the stable state +1. So this was done by all these references I presented before. But what is, so let me formulate the problem which we would like to address. Suppose that at time 0, you start from this configuration -1, then define a time scale theta beta. Consider your process at this time scale theta beta. So psi will be the process in the new time scale, the time scale in which you need to observe the system if you want to observe a jump from -1 to +1. And what would be to prove metastability will be, well, I want to project that process. Say in this case, I want to observe the process only at local minima, say. So that will be, so you remove from your state space many configurations, and now you want to observe the dynamics only when it hits one of these local minima, and then prove that the dynamics that you just defined, which is a shrinked one, converge to some Markov process YT, which describes the evolution among these local minima, or maybe along these two configurations, -1, +1. And since you're removing, so let's say that you want to study only these phenomena in which you start from -1 until you reach +1, well, so that you're removing from your state space all configuration but 2, what we would like to say is that in this time scale, theta beta, you don't remain a long time in these states that you removed. So if you fix any time t, chi will represent here in this talk the indicator function of this set, delta. So you remove these configurations. Well, you have to show that what you removed, it's not very important, which means that the total time you spend on this set for between 0 and t, it's negligible, will converge to 0. So that will be one possible, one formulation of the problem which we want to address. So that concludes what I want to say about the global dynamics on the Ising model. So let's turn now to a second example, which is the condensing zero-range dynamics. So now lambda L will be L size. There is no geometry here. and you want to describe the evolution of particles on this set. So the set of configurations will be n to the power lambda L. And I will represent now a configuration by eta. So eta x will represent the number of particles at site x for the configuration eta. And the dynamics can be described as follows. Well, you first consider a random walk on lambda L. So these are the jump rates of this continuous time random walk in this set. And I will assume that this random walk is irreducible. And then I'll fix a function, g, which is defined on n, and it's equal to 1 at 1. And for k larger than 2, it will be k divided by k minus 1 to a power of alpha, where alpha it's a fixed parameter larger or equal to 1. So, so here is a picture to illustrate the dynamics. You have at x four particles. So one of them will jump to y at a rate which is equal to g of 4, since there are 4 particles, times rxy. So this is the rate at which one particle jumps from a site x to a site y. So this defines the dynamics. And you see that this dynamics is conservative. So the total number of particles is conserved. So the ergodic components of these dynamics will be represented by lambda n. It's all configurations with n particles. So in this talk, L is fixed. So the total number of sites is fixed. And n will converge to plus infinity. So the number of particles, it's diverging. So I hope that the dynamics is clear. And there is a phenomena, a very interesting phenomena, which occurs when you, for these dynamics, you see that in these dynamics, so gk represents the rate at which one particle leaves a site. And you see that this rate decays with the number of particles on that site and converge to 1 as k tends to plus infinity. So the more particles you have, the slower they jump from another site to another site. And well, and this fact gives you the following phenomena for these dynamics, is that you have condensation which is occurring. So since the random walk is irreducible, you have a unique stationary state. And to describe this stationary state of the zero range process, let me assume from now on that the uniform measure is the stationary state for the random walk. You could have something else, but let's, well, what I will say doesn't depend on this assumption, but it's much easier to explain what happens under this assumption. So let's assume that the uniform measure is stationary for the random walk. And let me define A as an. It will be equal to n for n larger than 1, and 1 if n is equal to 0. And so we have an explicit formula for the stationary state of the zero range dynamics. Zn is a renormalization constant, and well, the measure of configuration, it's just given by this product where alpha is the parameter I introduced. Okay, that's not very important. What's interesting is this condensation phenomena I was talking about. So it's not exactly true what I will say, but it's essentially true. You need some further assumptions on Ln, but okay, I don't want to bother with that. So let's say that Ln is any sequence which converge to plus infinity as n goes to infinity, but at slower rate than n. And now defines this set, Exn. So this is the set of configuration in which you have at least n minus Ln particles at site x. So since Ln is small, in this configuration, essentially all particles are sitting at site x. And what one can prove is that the measure of this set converges to 1 over L. L, remember, it's the number of sites. So this is telling you that, well, with essentially total measure with respect to the stationary state, all particles are sitting on one side. So this is called the condensation phenomenon. You have, even if you start with an equal number of particles at each site, if you let your process evolve for a long time, at some point you'll see essentially all particles sitting on one side. So there is a condensation which provoked by these dynamics. which is a quite interesting phenomena. And so let me define En as the union of these sets Ex. So the measure of En, it's converging to 1. So let's say that Dn, it's the complement of En. So the measure of delta n on the stationary state, it's converging to 0. And note that, of course, En, it's very tiny. So if you count the number of configuration on En, you divide that by the total number of configuration, this is converging to 0. Nevertheless, the measure under the stationary state, the measure of En, it's converging to 1. And now you'd like to investigate this evolution, right? Maybe you start at time 0 with all configurations sitting at site 1. You let the process evolve. What you expect is that at later time, all these particles will sit on some configuration Y. And you like to ask, well, what is the time scale at which you observe such a jump? Or, what is the dynamics which describes the evolution of this condensate? And therefore, now I reach the point in which I introduce a general setup in which to describe these two phenomena that we presented. And under this general setup, we will state a theorem, which we just proved with Insuk, which is the next, which will present the next talk, and Diego Marcondes, which is from a student from the University of São Paulo. So the general framework, I would use essentially the notation I just presented for the zero-range process, but you can think also on the Ising model, in which n will be replaced by beta and En by the set of local minima of the Glauber dynamics. So you have a set. This set is divided in two sets, one which concentrate the stationary state and the other one which is negligible with respect to the stationary state. Then what we want, so we have a Markov process taking values in omega n, and you would like to have a synthetic description of this process. So in the zero range, so I'll be addressing to the zero range model, but you can think of the Gibbs if you prefer, of the Glauber dynamics for the Ising model if you prefer. But what you want to do is you want to present a synthetic description of this process eta. What does that mean? Well, I want to introduce a function phi, which is defined on the old set, and which takes value in a much smaller set. So in the case of zero range process, this set has L plus 1 points. In the case of the Gibbs, of the Glauber dynamics, well, you have a small number of global minima. And so you project these state space in this smaller space. So in the set Ex, you give the value X to the configuration eta. And note that you give, therefore, the value 0 to all configurations which are on the set delta. And now you consider the space, well, the evolution of this projection. So this is the state space, it's much smaller. Most of the case, Y and T will not be a Markovian dynamics because you're projecting a Markovian dynamics. So it won't be Markovian. And so what do you expect to observe? Let's say that we are in the zero range process, that you start with configuration in eta 1. So essentially all particles are sitting on site 1. What you expect is that you'll remain there for a very long time, until at some point that some particles, so that you hit the set delta n, and there you'll do many small excursions to this cell, so to this set. So you'll go to delta n, you'll return to the E1, you go to delta n, you return to E1, and that will create these jumps between 1 and 0 because you're projecting delta to 0. So you jump many times in a very short intervals from one to the other, and then you reach the interior of E1, say, and there you remain a very long time until you go back to delta, but maybe at this time, well, instead of returning to 1, you go to the set E3 and you remain there for a very long time and that. So if you want to prove that Y and T, so this is a typical path trajectory of Y and T. So if you want to prove that Y and T converge in the scalar topology, there is no way because, well, these small jumps from 1 to 0, from 3 to 0, forbid this convergence. So what you want to do is you want to perform a surgery in your path in order to remove these small jumps. And this is what we do by considering the trace process. So remember, for the Glauber dynamics, what I said, well, we want to study the evolution of these dynamics only when it hits local minima. So this is a formal way in which you can do that. So let's say that you fix a set F. So F here can be either En in the zero-range process or the local minima in the Glauber dynamics. And you first compute the total time at which you spend on this set F. So this is the total time from 0 to t at which your process spent at this set F. Now you define the inverse of this function, so this is called S, and you just change the time of your process by S. So you define a new process, an F of t, which is given by this expression. And what's very nice, so we call that the trace of the process eta on the set F. And here I draw a picture because, well, to make it clear what I mean. So let's say that the set F, it's formed by these 2 points, A, B. So here's the set omega n, and here's a trajectory. So say that you started from A, you remain at A, an interval of time t1, of length t1, then you jump out of the set F, jump again, you return to the point A, where you remain at time t2, jump out of the set F, you return to the set F at B, and go on. So TF, which tells you the total time you remained at F, will have the following, well, will be given by that. You stayed at T1, so this is T1. So you remain an interval of time outside. So T didn't increase in this interval. Then you go at T2, you increase, then you remain fixed in this interval, then you increase and so on. So what is the trajectory of the trace? You just remove all these times at which you spend out of your set F, and you pull back the times at which you stayed on the set F. So here's the trajectory of the trace of eta on F. So you remain at A for a time length of T1 plus T2, then you jump to B, and where you remained at time T3, and so on. And what's very nice about the trace process is that it's a Markovian dynamics. So this is a Markovian dynamics. That's nice. The problem is that the rates at which you jump for the trace process can be expressed in terms of return times only. So the rate at which you jump for the trace process from eta to psi, it's given by, well, let me represent by lambda eta, the holding time for the original process at eta. So we multiply the holding time at eta by the probability that you return to F at X. So H plus F is the time at which you return to F, and H psi will be the time at which you hit psi. So the rate is given by this formula. It's the probability that you return at F at psi times the holding time at eta. And of course, well, it's usually difficult to get explicit expression or to estimate these hitting times. But nevertheless, well, you have a Markovian dynamics. So what you want to do? Well, first you want to change your time scale, because you know that, well, if you want to observe a jump from one local minima to another local minima, you have to wait a very long time. So first you change the time scale of your process. So let me call psi t eta at this new time scale theta n. Let's consider the trace on these set E. So let me represent by psi E the trace of the process psi, so which is the process speeded up, and the trace at the set E. So this is a En valid Markov chain, continuous time Markov chain. So now you project these trace process on the set lambda L. So this is a Markovian dynamics, which is En valid. So delta n does not appear anymore. So you project now these dynamics, and you define this process YNT. So YNT, it's the projection of the trace process. And what you'd like to do it's to show that this process y and t converge to a Markovian dynamics. And then you would say, well, that this Markovian dynamics describes how the Ising model evolves among the local minima, or it describes the evolution of the condensate on all L sites. So what we did in 2010 with Joel Beltran is that we provided conditions all based on potential theoretic objects, the capacity, to ensure that y and t converge to yt, so that there exists a process yt such that y and t converge to yt, and moreover, that you don't spend a long time, you spend only a negligible amount of time on the set delta n. So for all del t, for all initial configuration on the set en, well, the total time you spend on delta n, it's negligible. So we have sufficient conditions, we obtain sufficient conditions to prove that. Now, the result I want to, okay, and this was applied to many, many models. And I don't want to spend time on that, but okay. And there are many people involved on this project. So here are some of them. I hope I didn't forget anyone. And if you want to look, well, I wrote a survey last year on probability surveys. So there we describe these results and this theory in more detail. But so the theorem I want to present you today, and which, as I said, it's a joint work with Ising, Seo, and with Diego Marcondes, is that, well, if you have two conditions, then these are two sufficient conditions to ensure the convergence of yn and the fact that you spend negligible amount of time. So let me state the hypothesis of this theorem. So there are two conditions. The first one, well, if you read it, you don't understand it, but I'll try to explain. So we want to assume that there exists a positive lambda and a generator of a lambda L valued Markov chain, continuous time Markov chain, which has the following property. If you fix any function f on lambda L, and you define G lambda as lambda minus L, so L is this generator, applied to f. So you define this function is defined on lambda L. Now you project, well, you pull this function to the space En or omega n by saying that, well, I want this function to be equal to G of x on the set Ex and to be 0 on the set delta n. So now Gn, it's a function defined on omega n. Now solve the resolvent equation for this Gn. So let me define Fn as the resolvent equation of these associated to this Gn. And the condition is that, well, the solution of this resolvent equation, it's very close to the function f on the site Ex. Okay, so let me try to explain this hypothesis. Well, first, what's behind this condition? Well, this condition will hold if the process equilibrates in which each well before jumping. This means that, well, you have these wells, which are the sets Enx. And as I said, you expect the Z-range process to remain a very long time in these sets before they jump to another well, another set Ey. If you observe the process, so if you take the, if you restrict your process to Ex, so this is called the reflected process at Ex. And this is done by forbidding jumps from Ex to outside the Ex. So you consider your dynamics restricted to the set Ex, assume that it's irreducible, and, well, you have a mixing time for that process. So what's behind this condition is that the mixing time inside the well is much faster than the time scale theta n at which you need to observe the process in order to see a jump from one well to the other. So if that condition holds, this hypothesis should hold also. And what you have to how to understand this condition is take a function g, forget about the definition of g, take a function g, which is constant on each well and 0 on delta n. Now solve this equation. What I claim is that if this mixing condition inside the wells holds, is that this function fn will be constant on each well. So if the mixing time on each well, it's much faster, if you mix, you equilibrate much faster in this well, then you jump from one well to the other, the solution of this resolvent equation should be constant, almost constant on each well. So you take a function g, which is constant on each well, you solve the resolvent equation. What I claim is that the solution should be essentially constant on each well. And well, by proving that, you'll find the constants that f, the value of these constants, so the value of the constant at which describes the value of f on each well. Once you know that, then you can find what is Ly. So because you know the value of f, now you have to find the L, which turns this equation correct. So this is the way you should understand that. By saying that, we are saying that the solution of this equation, it's essentially constant in each well. And once you prove that, you find also the generator of this reduction of your process, the generator of this lambda L valued Markov chain. So this is the first condition. You see that delta n almost doesn't appear in this condition. Well, the second condition tells you that delta n has to be a small set. In which sense? So let me represent by each x the union of all the wells different from x. And let's recall that HA is the heating time of the set A. So the second condition tells you that, well, between, so this is the time at which you reach a new well. So in this time interval in which you start from a well until you reach a new well, the proportion of time you remained in delta n is negligible. So this is the second condition. So the maximum over all possible configuration eta, that the total time you spend on delta n before you hit a new well is negligible. So under these two conditions, this is the theorem we just proved, is that what I presented holds, which means that if you take yn as the projection of the trace, then it converges, and it converges to y, which is the Markov process associated to the generator Ly, which appeared in condition R1. And moreover, the time you spend in delta n, it's almost negligible. So this is the theorem which I wanted to present. I see that my time is essentially over, so I was hoping to be able to give you a sketch of the proof, but maybe it's time to discuss. So let me just tell you what we did. So yn, as I said, it's the projection of the trace. So we can prove that it converges to yt. To prove that it converges to yt, we have to show that this sequence is tight and it solves a martingale problem. And well, you can do that. Unfortunately, I don't have time to present it, but to prove it's not very demanding. So, well, thank you for your attention, and I hope it was clear. Thanks.
Okay, so let me allow people to unmute themselves, and feel free to unmute and join together in applause. And we do have time for questions. I know there's been some discussion in the chat, but feel free to just unmute and ask Claudio a question.
So let me ask a question. Could you come back to this slide where you have these conditions on the condition R1? Yeah. So this condition R1 is a sort of that's a sort of resolvent equation.
Yes, that's a resolvent.
And so now you see one way in which you can obtain information about resolvent equations is looking at coupling time. No? So if you start with two different configurations and you know that they couple, they merge together fast enough, that will give you information about solution of this type of equation. So
Yes.
have you investigated this type of connections? And
No, we just proved this theorem, so we didn't do anything about it, but I'm sure that if you have such a result that tells you that if you start from two configurations on EX, on a set EX, then they meet before they hit a new well, then this condition holds. What I think very nice about this condition is that it tells you, well, it gives you, you have an operator, and it tells you that, well, if the solution of these operators are almost constant, then you have metastability.
mm-hmm. Okay, thank you.
Other questions?
I have a question, if it's possible.
Yes.
Yeah. So have you considered or reflected on the case of conservative dynamics? So not Glauber, but Kawasaki dynamics for these types of problems?
Yes. So so this is one of the, so here, so we consider with Bruno Goisch, so the Kawasaki dynamics in 2 dimensions. So this, you start with a square of, let's say, pluses in a sea of minus, and you want to investigate the evolution of these objects. And what you prove that in certain scale, you converge to a Brownian motion. So there, the size of the cube, it's not fixed. It increases also with beta. It doesn't increase very fast. The droplet, it's fixed. Its size is fixed. It's a small droplet. And you can prove that this droplet evolves as a Brownian motion in a certain time scale.
Yeah, the problem I had in mind specifically was one-dimensional with a small applied field. So there are studies of Kawasaki dynamics with an applied field for spin systems with anomalous scaling.
No, well, that we never looked. I don't know.
So that's kind of, that's in some sense, that's the issue of when you perturb away from the variational free energy picture and you don't have an underlying free energy. It's just the question of how do those techniques you have cope or adjust to perturbations, even small perturbations away, because the anomalous scaling is for any size of applied field. It's not a threshold, but the minute you switch on an applied field, no matter how small, the scaling changes.
Yeah, that's an interesting question. We never considered it. So yeah, maybe.
Okay, maybe I write to you.
Yeah, to think of it.
Thank you.
May I ask a question?
Yeah.
So concerning so the last theorem, there are so these two conditions, R1 and R2. Did you check these conditions for which models? So for which model did you check this condition?
This is what,
the previous list of applications.
Exactly. So two things. First, with Insuk and Diego Marcondes, we proved it for critical zero-range dynamics. So one result. Then what I claim, it's still not proved, but what I claim is that if you remember in the paper with Beltran, we had 3 conditions which ensure that these theorems hold. And these were the conditions that people used to prove. Mm-hmm. What I claim is that if these 3 conditions hold, then this one also holds. So this is weaker than the other 2. So we could extend. So that means that if you take the inclusion process, for instance, or the zero-range critical, supercritical zero-range, this condition R1 in particular holds.
Okay.
Yeah,
this is not yet proved. This is not yet proved. I mean, we need to write it down.
So let's all thank Claudio again for a very nice talk.
Thank you. Thank you.
And we'll take a 5-minute break, and then we'll continue with Insuk's talk just after the hour.
Can you hear me?
Yes.
Yeah.
Ah, great. So how is IMPA is going on? Is this still closed or is now open?
Yeah, it's still close. Huh? Well,
Here.
Ah, yeah. I mean, is
No,
there
no,
any?
but we don't have classes.
Uh-huh.
Everything is online until March.
Until March?
March, yes.
Oh. Mhm. So you just started summer, right? So summer might be much better than winter.
Yeah, the situation is not that bad. In the number of cases, it's decreasing, at least in Rio.
Uh-huh.
So schools reopened,
Mm-hmm.
but well, they will close by beginning of December because it's vacation time.
Mm-hmm.
okay, so before we start, let me just remind you that you can ask questions in the chat, then we will pass them to the speaker. And also let me remind you that in case you have an unstable internet connection, you can also watch the lecture on the YouTube channel of the One World Probability Seminar. Okay, so now let me introduce Ising Seo from Seoul National University, who is going to give the second talk of today about metastability of stochastic interactive systems.
Thank you for introduction. Yeah, thanks for invitation. In the previous talk, Claudio explained the general framework regarding the study of metastable behavior of random dynamical systems. In this second talk, we are going to see more specific examples to see how we can apply the general theory. In particular, two models that we are going to see is similar to Claudius one. The first one is Ising model on two-dimensional lattice at low temperature regime, and the second one is condensing zero energy process. But we are going to look at them more in more detail. So let me start with the Ising model on two-dimensional lattice. We can, even if Claudio introduced this notation before, but I'm going to redefine them for the completeness of presentation. Okay, we consider an Ising model on large two-dimensional lattice box lambda denoted in this figure, denoted by k the side length, and we shall put either plus or minus on each vertex and call this resulting object configuration. So a spin configuration will be denoted by sigma, and where sigma x represent a spin at a site x. So sigma x is either plus or minus 1. In this talk, we shall use some graphical simplification. Instead of looking at this complicated plus-minus configuration, we take a dual lattice, so that the original vertex become a center of dual lattice box. Then we paint each dual box by red if the corresponding spin at the center is plus, and by white otherwise. Namely, the red region, now you don't need to look at this plus minus sign. Now it suffices to look at this red region. And this red region represents the cluster of plus spin, and this white one represents cluster of minus spin. So this is a standard way of looking at the Ising configuration. Keeping in this illustration in mind, let's return to this definition of Ising model. So Ising Hamiltonian is written in this way, where the first summation represents the interaction between spins, and the second term, so here H denotes external magnetic field, so this is external field part. Now the Gibbs measure associated with this Ising Hamiltonian is called Ising measure. Here beta is inverse temperature, and the G beta is the partition function, turning this one into a probability measure. Our concern is the situation where beta is very large. So beta is inverse temperature. So beta is large if so that the temperature is quite low. So in this regime, the two most important configurations are this plus configuration and minus configuration. We can observe that if H is greater than 0, this plus configuration, which is configuration filled with plus spins only, is the ground state for this Hamiltonian, because it minimizes the first summation as well as the second sum simultaneously. If H is negative, then this minus configuration is ground state, but we neglect that situation. We assume without loss of generality that H is non-negative. If H is 0, so this external part disappears, then both plus and minus configurations are ground state for this Hamiltonian, since it minimizes this summation. So our main concern is on this second case. Claudio focused on this first case, but in this talk we are going to see the second case for which there is no external field. So in this case, I would like to mention that this Ising Hamiltonian is nothing more than this parameter of the red cluster. As you can see, this is exactly equal to this length of this parameter. Then this is a very nice simplification of this Ising model. So when you look at this figure, you can immediately compute the energy of this configuration, energy represented by this Hamiltonian. This is definition of Ising model, and now we are going to look at the dynamics. We consider a Glauber-type dynamics associated with the Ising measure introduced above, introduced before. which is continuous time Metropolis dynamics. Here, sigma superscript x denotes configuration obtained from sigma by flipping spin at x. So the dynamic is easy to describe. We assign Poisson clock at each side, independent Poisson clock at each side, and flip the spin at site x with the rate given in this way. So this is a standard Metropolis dynamic. So more precisely, if the spin, for example, let's try to flip this spin. Note that flipping this spin does not change the energy because it does not change the parameter of the lead cluster. So in this case, if the flip does not change, does not increase the spin, then 1 here is the minimum one. So that you update this with rate 1. On the other hand, if you update this spin, then it will increase the energy by 2. So this is 2. So the first one is the minimum one, and therefore updating this with exponentially small rate. Note that beta here is a very large number. So if this is positive number, then this first one is exponentially small. Hence, dynamic tends to lower the energy because it has exponentially small rate to jump to the configuration with higher energy. This is critical feature of this Metropolis dynamic. I also would like to mention that we can write down formal generator of this Metropolis dynamic in this way, but the precise formula is never important in this talk. I also would like to say that, of course, Ising measure is the invariant measure for this dynamic, and this dynamic is indeed reversible with respect to Ising measure. Now, this under this dynamic, this minus configuration and this plus configurations are stable. Roughly speaking, if we form a small cluster of plus spins from at this minus configuration, then we will return to the minus configuration instantaneously, since the dynamic tends to lower the energy, so that you will return to this minus configuration. The same happens at this plus configuration, so they are stable. However, if we wait for long enough time, then we can observe a transition between these two configurations, since the dynamic is just irreducible. Such a rare transition between these two stable configurations is called the metastable transition, and our main concern is to analyze such a metastable behavior between plus and minus configuration. So among the many questions, I extract two primary questions on metastability of Ising model. The first one is Erin-Kramer's formula, which is a sharp estimate of this kind of expectation. Here, tau plus is heating time of plus configuration. And so this is mean of the transition time from minus configuration to plus configuration. Here, I assume that H is non-negative because otherwise plus is no longer ground state. If plus is not ground state, then this expectation is not relevant object to be estimated. So for if H is greater than or equal to 0, then this mean of the transition time from a metastable point to a stable point is an important object to be estimated. Another question is, of course, Markov chain reduction. This is relevant when H is 0, because in that case, we have two ground state, plus and minus. So there will be a successive transition between these two metastable configurations. So we want to describe this successive metastable transition in terms of Markov chain after suitable scaling limit. So that is was the topic of the first talk. So, yep.
Is it obvious that, or not that, if you get, let's say, close to everything plus, then you go to rigorously everything plus very fast.
What do you mean? You start from plus?
No, okay. Let's say that you start from minus and you want. I think about this mean transition time that you wrote about, no? That the time that you need to go from everything minus to everything plus.
Yeah, everything minus to everything plus, yes.
Yeah, and but I was wondering if it's obvious or easy to prove that if you go to, let's say, not everything plus, but almost everything plus, then you get very quick to everything plus.
Yeah, sure. So yeah, so but so if you enter the domain of attraction of plus configuration, then you will immediately go to the plus configuration. So that is your answer is here. So if external field is positive, then metastable transition is characterized by critical drop-net. So if you form critical drop-net, then you enter the domain of attraction of a plus configuration. So you immediately go to plus. Is this answer?
You know, I was just wondering because maybe if you have very big box, everything plus is maybe not recurrent because you always have one isolated minus somewhere with the. But morally is like everything plus anyway.
I don't understand. Wow. So this is global dynamics. Why you can dynamics irreducible recurrent. So this is finite box dynamics. So
okay. So it's strictly finite. You're not sending the size of the box to infinity. No.
Yeah, the size of box is fixed.
Okay. Sorry. Yeah, that's what the point I was.
Okay. So yeah, if H is not non-zero, so if you have a non-zero external field case, if H is greater than 0, for example, we know the answer. We get no answer for dimension 2 or 3 by this sequence of OAuth. I think Claudio explained this work very well, so I'm not going to repeat this. So, however, for H equals 0, many questions are still open because we no longer have a critical drop-net, and the energy landscape is much more complicated than this positive external field case. So our concern is this zero external field case, and therefore, from this moment on, I'm going to assume that H equals 0. For H equals 0, the only previous work is done by Nardi and Joka in recent paper, at which for dimension 2 and there is no external field, they use some pathwise approach to metastability to get a large deviation type estimate for this mean transition time. We in our recent work, we generalize this estimate in 2 ways. First, we show that this mean transition time is indeed of this form, asymptotically given in this form as beta goes to infinity. K is fixed. This large deviation type estimate just says that this prefactor given here is just a sub-exponential in beta. For example, polynomial of beta in beta is possible, but we characterize this that this prefactor is a constant, which converges to 1/8 if you send k to infinity. And there is a complicated expression for ck, but I did not write it here because there is no intuition from this constant. Moreover, we can show that the trace process on this minus spin and plus spin, speeded up by a factor of this exponential scale, converges to a Markov chain with the rate given in this form. So that we also have a Markov chain reduction for this metastable behavior as well. Even if these two statements assume the periodic boundary condition, but we can handle open boundary condition as well. So k should be large enough number, but is fixed. Now, so this is the main result of the first part, and I'm going to explain how we can prove that. So the strategy for the proof is based on a connection to potential theories. I'm going to briefly review the potential theory and explain general strategy. So two important notions in the study of metastability is equilibrium potential and capacity. So let's assume that A and B are disjoint and non-empty subset of configuration space. And then equilibrium potential between A and B is a function whose value at sigma is the probability that the process Metropolis dynamics starting at sigma hit the set A before hit the set B. So this is a simply defined function. So by definition, you can observe that this function is 1 on A and 0 on B. So if you start from A, then you will immediately hit A before B. So this probability is trivially 1, and vice versa. So capacity is just a Dirichlet form of this equilibrium potential, where the Dirichlet form for Metropolis dynamic is written in this way. But I'm going to stress that this complicated formula is never important in this talk. You can just think that, there is a Dirichlet form. So this Dirichlet form of equilibrium potential is capacity. This capacity is important. Capacity and equilibrium potential are important because they can answer both of the questions that I suggested before. For example, there is a formula for mean transition time, which can be written in this way. And you can easily observe that this is asymptotically equal to this one, which is equilibrium invariant measure at minus configuration divided by capacity between minus configuration and plus configuration. This has been found by Bobiev, Gelad, and Klein. And for Markov chain reduction, let's denote by R beta the jump rate of the trace process on minus and plus, which is defined in first lecture. Then this jump rate can be expressed in this manner, which is inverse of the first one. So in order to prove the scaling limit for the trace process, what you have to do is just estimate of this quantity. So we know that from definition of Ising measure, you can easily check that this probability on minus configuration is asymptotically 1/2. So that in order to answer both of these questions, so what you have to do is to estimate the capacity between minus and plus. And this is the main thing that we have to do. In next few slides, I'm going to explain the general strategy to estimate the capacity between two configurations, two sets. So here I regard this minus configuration and plus configuration as a singleton. So the estimate of capacity is divided by upper bound and lower bound. So for upper bound, you have to use Dirichlet principle, especially when the underlying dynamic is a reversible Markov chain. So for reversible Markov chain, you can express capacity as infimum of Dirichlet form of F, where F is 1 on A and 0 on B. So this principle provides you a way of estimating upper bound. Because if you take any function F and satisfying these two requirements and compute Dirichlet form, then you immediately get upper bound for capacity, right? However, you want this upper bound to be sharp, then you have to take F as a approximation of optimizer. But we know that the optimizer is equilibrium potential between A and B. So what you have to do is very clear. You have to find a nice approximation of equilibrium potential, which will be denoted by H bar AB, and then compute this Dirichlet form of this approximation. Then you will get nice sharp upper bound, provided that you find a nice approximation. This is the strategy for the upper bound. The lower bound is slightly more tricky. to explain the lower bound, we have to introduce a flow structure. So to define flow structure, we have to define a graph structure on omega space of configuration. We connect two configuration sigma and zeta by a directed edge if jump from sigma to zeta is positive. If a jump from sigma to zeta is positive, then the reverse jump is also positive, possible by the reversibility. And flow is nothing more than antisymmetric function on the space of this edge. So this is flow because phi sigma zeta represent the flow coming from sigma to zeta. So this should be minus of flow coming from zeta to sigma. So that's natural notion, which is flow. One important example is this one. So if you have any function f on configuration space, then flow psi f is defined in this way. You have to check why this is antisymmetric function. So you have to switch sigma and zeta. If you switch sigma and zeta, then the first part doesn't change because of reversibility. Detailed balance condition ensures that this part doesn't change, but this second part might be changed, multiplied by minus. So you have you can check that this is indeed antisymmetric function, so it is flow. So this is important example. And there are two important notions in the study of a flow structure. The first one is flow norm. So if you have a flow, then you can define this kind of weighted L2 norm as the norm of flow. There is a huge theory behind this, but today I'm not going to touch this theory regarding Markov chain, but just keep in mind that there is a flow structure. There is a norm structure on this space of flow, and the divergence is defined by summation of divergence of flow at sigma is defined by the sum of flow coming out from sigma. So it is defined in this way. I think there is a chat, no? Oh, I don't know. I cannot see. Okay, I will answer later. So there is a flow norm and there is a divergence. Let's this is a very brief view of a huge theory. So how to prove lower bound? You can prove lower bound in this way. There is an inequality of this complicated form so that you can bound the capacity from below by expression which is involved with the flow norm and divergence of flow. And we know that the equality for this lower bound holds for this flow psi of HAB, where psi f is defined here. So if you insert equilibrium potential here, then you get optimizer for this inequality. Now let's assume that you have a nice approximation of this equilibrium potential, which is denoted by H bar AB. Then you want to try phi as psi of this function here to get lower bound. But in real application, you have to modify this flow a little bit. But this procedure is usually easy. So you modify a little bit, then you get, and then you insert this flow to here, then you get a sharp lower bound. So there is classic Thomson principle, but I modify this Thomson principle a little bit in this paper because this Thomson principle is hard to use because divergence-free condition. So this inequality holds for any non-zero flow, so it's very convenient to bound the capacity from below. So summing up, what we have to do is very clear. What you have to do is to construct a nice approximation of equilibrium potential. Then the Dirichlet principle immediately gives you an upper bound, and this generalized Thomson principle gives you immediately lower bound, where phi here is a modification of this flow. in this strategy, the only model-dependent part is the first one. You have to make this approximation, but once you have that, you are done. Here, of course, you should, model is used at step 3 in this modification procedure a little bit, but that is not important. There's some similar but more complicated strategy for non-reversible case also is known, but it's more complicated. Today, I'm going to focus on reversible case only. So now I'm going to briefly review some model-specific computation. Let's go back to this Ising model. So in order to construct equilibrium approximation of equilibrium, what we have to do is construct the approximation of equilibrium potential. To that end, we have to understand the energy landscape between this minus configuration and plus configuration. Nardi and Joka showed that the communication height, so energy barrier between this minus configuration and plus configuration is exactly 2k plus 2, which means that any path connecting minus configuration to and plus configuration by successive flip of spin must visit a configuration with energy 2k plus 2. We refine this estimate by characterizing all the said paths, all the paths which connect minus and plus and does not exceed energy 2k plus 2. For instance, we show that any such path must visit these kind of canonical configurations. So this is configuration with 2 lines of plus and 3 lines of plus, 4 lines, 5 lines of plus. Note that, so here we assume the case is just 7. And note that we do not need to visit 1 line, a configuration with 1 line of plus and 6 line of plus. So since we assume the periodic boundary condition, the parameter of this configuration is just a 2k. All these configurations are 2k, but any update from this these canonical configuration lead us configuration with energy at least 2k plus 2. So the energy landscape must look like this. We should note that there is no critical drop-net. Instead of critical drop-net, we have a huge set of saddle plateau, for each transition path. So it is now we have to analyze what happens between these canonical configuration. So let us first look at this bulk of saddle plateau. Here, what happens is very simple. In order to make transition from these 2 lines of plus to 3 lines of plus, what you have to do is to make a protuberance, and then you expand this protuberance to size 2, 3, 4, 5, 6, and you have to reach this configuration. This is the only way of doing the transition from here to here. And moreover, if you, for example, if you look at this configuration, then you have to go to either this configuration with the protuberance with size 3 or protuberance of size 5 with equal probability, and probability that all the other update, all the other flip is exponentially small, so that we can neglect them. So summing up, you can, the behavior of Metropolis dynamic between this canonical configuration and this canonical configuration can be approximated very well by a symmetric random walk on this space of this simple structure. So it is relatively easy to understand the behavior of dynamics at this bulk of saddle plateau. However, on the edge of saddle plateau is a little bit more complicated. In order to go from these 2 lines of plus to minus to this minus configuration, what you have to do is to first make this protuberance of white, and you have to expand it as before. However, there are many irregular shapes between these two, and all these configuration has have energy 2k plus 2. For example, instead of expanding this protuberance by size to a size 3, you can flip this side to get another configuration of a size 2k plus 2. What we observed is that all these configuration have the same feature, which is that this flipped side has certain tree structure. So what we can do is that the dynamics of Metropolis dynamics here, we approximate that as random walk on this space of subtrees of ladder-shaped graph. So this complicated. I'm not going to say detail, but what we did is so with this analysis, we can construct the approximation of equilibrium potential. So at the bulk, using this simple random walk, you can construct the approximation of equilibrium potential. And in the edge, we can use this random walk on subtree to make a approximation. And in the remaining part, we set just 1 here and 0 here. If you start from here, then you have dominating probability to hit this minus configuration before plus configuration. So you can easily set H as 1 and 0. So with this, we can construct this approximation of equilibrium potential, and we are almost done. And now you can get this kind of upper bound immediately. Now we have to define a test flow. So for test flow, since you have a nice approximation in this saddle plateau, you define phi in this way. But this is flow from this side to this side only. But we want to flow coming from minus to plus. So we construct some modifying flow around the neighborhood of these minus configuration and plus configuration to construct a flow from minus to plus. So this is a way of constructing a way of modifying to get a test flow phi. And with this phi, we get the lower bound along with generalized Dirichlet Thomson principle. So we have a lower bound and upper bound where these bounds are same, at least asymptotically. So we can conclude that this capacity is asymptotically this number. This concludes the proof for two-dimensional Ising model. In that paper, we also handle three-dimensional model, which is much more complicated energy landscape than this one. And we also handle patch model with the zero external field, as well as Bloom-Kapel model with zero chemical potential and external field. For three-dimensional model, we have very similar type of result, and the energy barrier is changed from 2k plus 2 to 2k squared plus 2k plus 2, and the limit for ck is now changed a little bit. So this paper is not yet in archive, but it's uploaded in my personal web page as a draft, and it's a very complicated paper, so it's more than 100 pages. So we are still writing the paper right now. Okay, now let's turn to the second model. I'm running out of time right now. Okay, which is condensing zero-range process. Since Claudio already introduced it, I am going to be very fast in the definition of the model. So this is interacting system of random walk on this discrete torus. I'm going GL discrete torus of size L with a certain rate. So we can denote configuration by space by Hn, where now eta denotes the particle configuration and eta x denotes the number of particles at site x. So we assume that there are n particles. In this business, we are going to send n to infinity, but L is now fixed. And okay, so the zero-range process is a Markov process with the generator of this form. So that you send a particle at site x to site y with rate g at x rxy. Here, we are going to assume that Gn is approximately, asymptotically 1 plus alpha divided by n, so that, which means that particles are sticky, because if there are more particles here, since this is decreasing function in n, If you have more particles, and it is less likely to jump to the other side. So the particles, which means that particles are sticky, and alpha is a parameter denoting the strength of this stickiness. For the simplicity, we are going to assume that this underlying random walk is nearest neighbor random walk on discrete torus. So with a jump probability is p to the right and right side. So our result indeed holds for any graph with any random walk, but for simplicity, we assume that the graph is simple and dynamics is simple. So as Claudio said before, you can define invariant measure of zero range process, and this set denote Claudio write this one as E and X, but this denotes the set of configuration such that most of particles are concentrated at site X, and E is the union of EX, so that this is a set of configuration such that most of particles are concentrated at a certain site. So we say that condensation of particles occurs if this invariant measure, this set has asymptotically measured one full measure under the invariant measure, as in the first presentation. So now the question is whether condensation of particles always happen or not. So that depends on this parameter alpha. So there is a competition between this stickiness of a particle and diffusive behavior of underlying random walk, so which cause phase transition in alpha. So if alpha critical, so alpha critical here is 1. So if alpha is greater than 1, we observe condensation. But if alpha is less than 1, we do not observe condensation, but we observe the diffusive behavior. So if alpha is 1, the critical case, we observe condensation, but we have to take Ln here large enough to satisfy this asymptotic relation. For example, we can take Ln as n divided by log n to match this condition. So with our main concern here is alpha equal 1, but 1 here, okay. So this is condensation of particles. You can say that under the invariant measure, most of the particles will be concentrated on one site with dominating probability. Now let's look at the corresponding metastable behavior. To this end, let's assume that particles are spread over the discrete torus initially, and let's run the dynamic. Then by the condensation result before and the ergodic theorem, you can observe that condensation of a particle as if you turn on zero range dynamic, then particles will be concentrated on one side in the end by ergodic theorem. And this nucleation of condensate happens in the time scale of n square, provided that alpha is greater than 1. It is verified by Beltran, Hara, and Landim. We expect that the same thing happens at alpha equal 1 critical case as well, but it is still open problem. Now, what happens next is the following. If you form a condensation at site X, then because of the stickiness of particle, you will stay there for a long time. So this set EX is locally stable, and they are metastable, and they will be called metastable value. However, because of the recurrence of the system, if you wait long enough time, then you will observe a transition of this condensate to another site. So this movement of condensate happens at time scale theta n, which is n to the 1 plus alpha if alpha is greater than 1, and n square log n if alpha is 1. So this scale is larger than n square. But note that for critical case, this is slightly larger than this nucleation phase, and this implies that this critical case is a little bit delicate issue. So remember that theta n is given in this way. So we are going to speed up everything in theta n. Okay, our main objective is to get Markov chain reduction for this model, as Claudio explained. You start from zero range process, and you delete this excursion outside to get a trace process on E. So this is a trace process is obtained from original process by turning off the clock when you are not in the set E. So now you speed up your trace process by a factor of theta n, which is given in here, which is the time scale for the movement of condensate. And you define order processes in the first lecture, which denotes this index of well at which this speeded up trace process is located. The question is following. Markov chain reduction, we have wanted to show that this order process converges to Y for certain limiting Markov chain Y on GL, and this negligibility estimate, as Claudio explained. So the second one is just technical one. So we are going to focus on the first question. For this question, we know we have a strong guess on what this limiting Markov chain is. So this is Markov chain on GL with a certain rate, which is proportional to the capacity between X and Y with respect to this underlying random walk. Here CG is a constant depending on unit G, and L is the size of the discrete torus. So this metastable behavior with this limiting process Y has been widely verified. For example, for supercritical case, we know the answer very well. In this case, we use the potential theoretic method explained in the first part of my lecture to answer this metastable behavior. We completely answer this question. So, but in critical case, we cannot use this capacity estimate approach that I explained before, mainly because metastable value is too large. So we need alternative.
我那个就把那个第一篇那个论文就重新那个。
Okay, so it's impossible to use this capacity estimate approaches, so that we have to use different approach, and that is the resolvent approach that Claudio explained. So what we want to do is to prove this this theorem, which is indeed condition R1 of the first presentation. We consider this resolvent equation for zero range dynamic, and we want to show that this solution is flat on each valley, and the asymptotic value is close to fx here. So this equation, in this equation, Ln is generator of zero range process, and Ly is generator of limiting process Y. So this expression itself is not important, but important thing is that we want to show this kind of estimate. So the proof is divided into two steps. I'm going to explain how the proof is going on. So before jumping to this, I would like to mention that if lambda is 0, then this becomes a boson equation, and this approach using this boson equation is now famous and already known. But our method has a certain benefit over this boson equation approach, and I'm going to get back to this point later on. So let's look at this equation, and the proof is divided into two steps. First, I'm going to prove that this solution is flat on each value by showing that this is equal to each conditional mean on this value Ex. So this is conditional mean, but the expression is not important as before. And then second step, I'm going to show that this conditional mean is indeed close to fx. So by combining these two, you can show this one. Our benefit for considering this positive lambda case is concentrated on this first step. So let me explain how we can do that. So we can, for this first step, we can write down more general theorem, which says this. if you consider this resolvent equation of this form, where Gn is any uniformly bounded sequence of functions, then your solution here is flat on each value. That is what we are going to claim. I think that Milton already pointed this out in after this Claudio's talk. So key observation is this. The main benefit is that the solution of this equation can be written in this way, where tau here is exponential random variable independent of all the other randomness. So which means that thanks to this expression, you can observe that this theorem is closely related to the mixing of the zero range process inside the belly. Because if you start from eta, and if you mix inside the well, then instantaneously, namely if faster than zeta n, then you will forget this initial configuration instantaneously, right? If you mix faster than zeta n, then you will forget this one instantaneously, which means that this value does not depend on specific value of eta. So that is what we are going to use in the proof of this statement. So, okay, then we have to see in which sense we have a mixing inside the belly. So this is the belly, metastable belly. And we first show that the spectral gap of restricted process, the restricted process is the process, zero range process restricted to this region, which is obtained by excluding the jump from inside to outside. So it should be confined into this region. So if you do that, then we can estimate the spectral gap of that process, and which is Ln square, which is much smaller than zeta n. This implies that if this restricted process mix inside this well before zeta n, and the invariant measure for this restricted process is the conditional invariant measure on this value, which appears here. This measure, this is expectation with respect to the invariant measure for this restricted dynamics. Okay, so however, this is just mixing of restricted process, not the zero range process. In order to turn this into the mixing of the original zero range process, you have to couple this restricted process and zero range process with high probability. Then you are done. In order to do that, we define two sets in which one of them is smaller than the well and another one is larger than the valley. And then we constructed a superharmonic function in this region, satisfying these two conditions. And this harmonic function, along with the standard Ito type argument, says that if you start from here, if your process starting from here, then you will hit this bottom without escaping from this well. So there is a strong attracting force toward this bottom. And that is true for both the original process and this restricted process. So you will meet, these two processes will be coupled inside this deep blue region. So that is the way of proving mixing inside in the critical case. So this first step, we have to use reversibility, of course, because otherwise we cannot define spectral gap. And in this construction of a superharmonic function, we use uniformity of invariant measure. So that our result holds only for p equal to 1/2. Otherwise, we don't have any mixing result at this moment. So using this, okay, this theorem implies step 1 because in our case, the Gn is given in this way. So, and the probabilistic expression of solution that I said before reduce the proof to the verification of mixing inside the belly. And in our critical case, this local spectral gap estimate and attracting property to the bottom of the belly implies this sufficient level of mixing inside the belly so that we can verify this theorem. That is the story for step 1. And I'm going to review step 2 very fast. Sorry for spending too much time. So for step 2, there is a robust method for lambda equals 0. And this method also works for this positive lambda case. This method is developed by O and Reza Kanu in this paper for supercritical range process, and used to many other models, in particular metastable diffusions. So I'm going to briefly review what this method is. So what we wanted to show is this: you have a solution to this resolvent equation, then you want to say that the conditional mean of Fn is close to Fx on each valley. The idea is very simple. You multiply both sides of this equation by this one and summing over eta, where Hn is the test function of this form. Here it's interesting that this approximation of equilibrium potential appears again. So here you have to construct this approximation of equilibrium potential, not for estimating capacity, but for characterizing this conditional mean. So if you do this, and if you use a bunch of energy estimate and a lot of integration by part, summation by part, then you will observe, you can obtain this kind of expression, which immediately implies this estimate. This is proof for step 2, and this this part prove the condition R1 for of the first lecture. So we still have to prove R2 of the condition, but the R2 is indeed, we believe that R2 is true for critical case, so of course, but we cannot prove this one at this moment. But we proved a slightly weaker version of R2, and the additional attracting property that I mentioned before can replace this R2 to complete the proof of a critical case. This is the proof for the critical case, and this is the end of my talk. Thank you.
Thank you very much. So let me see.
Just let people unmute themselves.
Okay, very good. So now people can unmute themselves to thank Insuk for this talk.
Thank you.
So now you can unmute yourself and ask questions if you want to. So, okay, yeah, so want to say something? Okay.
So I have a question. May I ask?
Yes, Alessandra. Yes,
sure.
Of course.
You have this capacity from X to Y, between X and Y, depending on P. Okay, in your.
I see.
But which information do you have about the form of this capacity?
You mean this one?
Yes. So do you have some control, some information on this function?
So you mean which one? CG or capacity?
For the capacity.
We can
this function. Have you some information?
Yeah, we can compute capacity explicitly. This is capacity. You have a cycle of length L, and you have a symmetric random walk.
Okay. I'm a little tired.
Yeah.
Okay. Yes, of course. Sorry. Thanks.
So I have a question for you, Insuk. So in let's say when you want to this idea of using flows, it's kind of well developed in potential theory, right? And for example, when you look at a random walk, simple random walk in dimension, let's say, in dimension 3, when you try to construct a flow that it's a good approximation for this capacity, somehow the important, most of the contribution comes from around the points that
Yes.
you're looking at.
Mm-hmm.
Okay, so but then the difficult part is to kind of spread the flow in such a way that outside is not really. You don't use a lot of energy to construct the float outside I mean, far from this from the points that you want to look at. So how does it work here? It's similar. The difficulties are similar or are different.
So it depends on model, but that is exactly what happens in critical zero range process. So in critical zero range process, your valley is too large. So it is hard to spread out this flow over the valley. But in usual case, it is not difficult in metastable situation because you have very strong force to alter this metastable point.
Okay.
Unlikely so for three-dimensional random walk case, it's not recurrent, so it might be difficult to do that. Yeah.
Okay, so this is a question on the chat by Andres Shakar. So, is it possible to have a measure of goodness of approximation with H bar? It seems the proof in both cases rely on that.
Yeah, there is. So this is technical question. So what the important thing is that I didn't write it for, okay. So let me, can I use, okay. So another feature for this equilibrium potential is that L generator is, I don't have a pen right now, sorry. So this is 0 on complement of A and B. So if it is good approximation, then it should be very close to 0. And if you take, for example, if you take absolute value and if you take invariant measure here, mu sigma, if this is smaller compared to the capacity, then your approximation is very good. So you have to measure the goodness of approximation in terms of this generator of L of H, which should be 0 for real object. I hope that this answers.
Okay.
I have a question, Milton. If it's possible to extend that for the case in which the square of the cube it's increasing,
For
in the Potts model that you presented, or in the Ising without.
So you want to increase the size of the box together with the.
Yes.
Yeah, that's next project that you are going to consider indeed. Yeah. But might be more difficult than this one, yes. I think, yeah, that is next project.
So now I remember something in Sukat. So now I can be a little bit more precise with the question I I asked at the beginning, okay? Because the question can be rephrased like this. So the plus and the minus configurations. So the values in this case, in the case in which you have zero field in the Ising model. So the plus and the minus, the values, are they recurrent or transient? And maybe I can rephrase: if you send the size of the boxes to infinity, do you expect the values to be recurrent, or do you expect them to be transient? Because that will change a little bit the strategy of proof, right?
Yeah. It should be. Yeah, it depends on the speed, but it should be maybe recurrent, I think. I'm a little bit. I'm not sure at this moment, but feeling is recurrent. Do you have any objection or?
No. It's just that I don't have any intuition about whether it's to design either of the two directions.
Yeah, I'm a little bit worried to answer because it is recorded right now, but yeah, I think that it's recurrent in my feeling. Yeah.
So there is one more question in the chat by Saida Marielo. So could you say something more about the coupling you mentioned at the end? This technique has often been used to prove independence of the mean metastable exit time on the initial configuration.
Yeah, so okay. Yeah. So what we can prove is this. If you enter this blue region, then you hit every point. So this set is cycle. So the once you enter this region, you hit all the configuration here before leaving this well with dominating probability. So that, which means that if you start from here, then because of this superharmonic function, you enter this deep blue region, and if you enter here, you will travel this region for a long time. This is small enough because epsilon here is small, so that and if you start from here, so that because of this, you can now assume that you start from this region, and if you start from here, then you do not escape this set in a short time scale. So that the original process and reflected process move together until. So the point is this. So this process makes before set n. The difficulty is the following. If you start from here, very close to the boundary, then okay, the reflect process hit this. If we, as soon as this process hit this boundary, and they now move differently, right? One goes to this way, and another one is reflected. So we don't want to this, and we want to say that this one does not happen before this mixing time scale. But if you start from here, you can do that because you do not escape this set before the time scale ln square. So you want to assume that you start from here, and we can do that because of this property. Because if you start from here, then you will hit this set immediately with the dominating probability. That's our strategy.
Okay, so if there are not other questions, let's thank Insu again.
Thank you.
well, and hope to see you next